For our independent project, we are focusing on our current location of Ithaca, New York, including Cornell University, specifically spanning the region of watershed that extends from Beebe Lake and following Fall Creek through the Ithaca Falls natural area to its eventual joining with Cayuga Lake as it opens from Stewart Park.
Lead contamination is a prevalent issue in the Ithaca area due to pollution from the Ithaca Gun Factory, which operated from 1885 to 1986. In 2008, sampling revealed lead levels of 69,800 parts per million in soil near Ithaca Falls, which is 175 times higher than acceptable levels. The city of Ithaca has had to constrict these areas as they're very dangerous to visitors, and there have been several efforts backed by the EPA to try to clean up this area. Our goal is to try to model a potential solution to lead contamination in the Ithaca waters.
Mitigating lead contamination is specifically important considering that much of Ithaca's drinking water is sourced from Fall Creek. Therefore, higher levels of these contaminants pose dangers to residents and visitors, as well as the larger aquatic ecosystem.
TSS, or total suspended solids, is a measure of water quality and is a dry way of suspended particles that are not dissolved in a sample of water. Turbidity is also a water quality measure, which refers to how clear water is. Therefore, the greater the total suspended solids, the greater the turbidity. Residence time is essentially the time a particle or an entity has remained inside of a volume. So for our case, we'll be using the total suspended solids as a way to estimate the resident time of lead in the water. TSS can be improved by increasing the resident time of water in order to give the solids more time to sediment out of suspension.
I'm here at Ithaca Falls, the river that we are going to be trying to vaguely allude to or model. There's the reports of the lead concentration around this area down off the cliff that I could not get to. There's been reports in the news, local Ithaca papers, 160,000 parts per million lead in this water. Somewhere, I think it's over there. Yeah. They're dumping all this lead pollutants into Ithaca Falls and then Fall Creek. So we're going to see if we can do something about that.
This map gives an overview of the lower Fall Creek area. The area below where I recorded my video has had soil lead content reported at roughly 70K to 160K parts per million. We will be modeling runoff from this soil, seeing if slowing the flow of the river is a viable way to cause the pollutant to settle before it reaches important areas such as Stewart Park. We'll be approximating a typical flow rate from Ithaca Falls using USGS data. I had gone out and taken samples from the points on this map described as point number 1 and 2, but was unable to use these samples to determine turbidity since the solids settle before I could get to the lab. Additionally, since Ithaca Falls site has had a large amount of soil removed, it is no longer as polluted as it once was. Due to these limitations, we are using the Fall Creek situation as inspiration to give our model realistic parameters for residence time, flow rate, pollution level, and so on.
We created turbid water using kaolinite, which is a clay mineral that we are using instead of lead. A spectrophotometer is an instrument used to measure the intensity of light absorbed after it passes through a sample at a certain wavelength. We're going to use this to estimate the total suspended solids and amount of clay left in our sample after going through experiment, which we will measure the absorbance of an unfiltered water sample from the effluent at a wavelength of 750 nanometers.
We will be using a setup similar to Lab 5 and attempts to model the plug flow reactor conditions of a river like Fall Creek. As we analyzed earlier this semester, a plug flow reactor model describes continuously flowing reactor systems where the fluid can be modeled as a series of infinitely thin, well-mixed sections that differ from each other. We will slow the flow rate and add baffles, representing various methods of slowing the river like weirs, dams, or ponds, until we can reduce the TSS and the X-fluent from our starting concentration to the EPA lead action level of 0.015 milligrams a liter, or another useful standard.
The overall goal of our experiment is to increase the residence time of the clay with baffles in our reactor to minimize the suspended sediments, improving the water quality of the system in the hopes of applying this model to Fall Creek for less contaminated drinking water across the area. Thank you for watching.